Let's wrap up this series on classification with a bit of advice. Welcome to this video on classification. My name is Kevin Fiesel, and I am the proprietor of Galaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. As we wind down this series on classification, I want to put up a conclusion video that gives you an idea of when to use all of the various algorithms we covered in the series. And please don't think that the algorithms we looked at are all of them. Oh no, there are plenty more in that cupboard, both in terms of classical techniques and neural network-based techniques. Still, even though we only looked at a subset of all possible algorithms, there are a lot of them here, and I think it's perfectly fair to ask, when would I use any or all of these algorithms? Well, let's impart some general advice before we bid each other adieu for this series. First, don't get stuck on any one algorithm. As we saw in the series, most algorithms behave roughly the same in scikit-learn, so you don't have to learn a lot of new mechanics to use a new one. This incentivizes trying out a variety of them for your task. We also saw that there are some cases in which algorithms may work really well, and in other cases they may not work well at all. So try out several algorithms for comparison before deciding if your task is impossible, or that you've made the best algorithmic choice you can. This leads to the second bit of advice. Make sure you have at least a passing familiarity with each algorithm before trying it out. One big example of this is k-nearest neighbors. As we saw in the prior video on multi-class classification, k-nearest neighbors can suffer from the curse of dimensionality, where we feed in too many pieces of information that are somewhat correlated together, and it causes the algorithm to select based on attributes of little practical relevance. But because we knew about this, we could view the results, anticipate that they might cause this problem, and react to it. After performing a principal component analysis, we reduced the number of dimensions to 3 and dramatically increased the quality of our model. Similarly, if you feed continuous data into a categorical naive Bayes algorithm, scikit-learn will let you do it, but will assume that each unique value is its own class, leading to poor results. You certainly don't need to be the world's foremost expert on an algorithm to make good use of it. But that said, every algorithm has its own foibles and expectations. Many algorithms also have hyperparameters that you should know about, as changing these may substantially alter the results you receive. These hyperparameters could include things like the number of trees, the maximum depth of a given tree, the number of neighbors, whether to perform Laplace smoothing, or the max number of iterations for convergence. You can typically run algorithms with the defaults, but your unique circumstances make it unlikely that those defaults are the best choice, or sometimes even a good choice. The third bit of advice I'll pass along is to spend some time doing pre-processing right. I showed off a little bit of it through the series, though the intent of this series wasn't to focus on the pre-processing of data. I might have a series on that in the future, as it is the most time-consuming task for a data scientist, and our results depend on whether we do it right. Now, I'll get into some specific advice. First up, as always, is categorization and regression trees, or CART. My advice on CART is, well, you probably want to use random forests or gradient-boosted decision trees instead. I suppose it is theoretically possible to land on CART results that are equivalent to the best that random forest, XGBoost, LightGBM could do, but we consistently saw significant gains when moving from CART to these more advanced tree algorithms. So let's talk about the rest of the trees. I like random forest a lot as an algorithm. I think it has a lot going for it. What it does not have going for it is its ability to scale. As your datasets get larger and larger, random forest gets slower and requires more memory. Well, let's get another edition of Story Time with Kevin here. Several years back, my predictive analytics team received an invitation to go to Microsoft's Redmond campus, with the goal being to solve a problem we had around classifying products given some taxonomy of categories. Okay, our database team got the official invitation, but we got a secondary invitation to tag along, and we got to meet some really cool data scientists, very smart people working at Microsoft, which enjoyed that a lot. Anyhow, we brought along our laptops, we brought some extracts of customer data, and we hacked away at it in a lab for several days. I turned it into a bit of a game, where each member of the team, which included our PM, we would all try out different algorithms and hyperparameters, and we'd attempt to get the highest overall accuracy in F1 scores. I would keep track of the scores on a whiteboard, and we had one big quasi-competitive event with a lot of conversation, recommendations, trying out different techniques, and doing research along the way. One of the algorithms that most of our team tried was random forest, and the problem was their laptops kept running out of memory while trying to train the model. Other algorithms would work, but random forest was a struggle. When one person did finally get random forest up and running, my recollection is that we ended up having to borrow some server in the Microsoft lab to do this, but it did perform really well. It also took up a large chunk of memory compared to the other algorithms that we tried. So, in that case, what's the alternative? Well, XGBoost and LightGBM. These are really good alternatives to random forest. They also require a fair bit of memory and compute time, though less than what random forest requires. And all three algorithms are typically in the same ballpark, which makes gradient boosting an enticing technique. You can have more rounds of testing or more sweeps of hyperparameters in the same amount of time for any given hardware. And that means you're more likely to find the right set of hyperparameters for the job. Now let's move on to non-tree algorithms. First up, k-nearest neighbors. KNN works best when there are few discontinuities in the data. By that, I mean that you have primarily continuous rather than categorical data, and you have some expectation that values will cluster together. It also works best when your neighbors are relevant. With continuous data, we typically expect neighbor relevance. A person who makes $80,000 in a year is quite similar to a person making $80,001 in a year in terms of purchasing power, and the two likely make similar decisions to one another, particularly compared to a person who makes $30,000 in a year or $5 million in a year. By contrast, categorical data only sometimes has an order to it. One example of ordered categorical data is maximum level of schooling, which could include as categories things like middle school completion, high school or GED completion, associate's degree, bachelor's degree, master's degree, PhD, etc. In that case, items in the next category over still have some level of relevance. We could expect that a person with an associate's degree would have more to do with a high school graduate or a person with a bachelor's degree compared to someone with a PhD. By contrast, assume that another dimension is the person's favorite color. In that case, we might order the colors lexicographically, such that blue comes after black and before brown. But we don't have any reasonable expectation that people who like the color blue are more related to people who like the color brown versus people who like the color green or orange or red. If your data is full of dimensions like those, k-nearest neighbors, probably not a good fit. Now let's talk about logistic regression. Logistic regression can work really well if you have very large data sets and independent features. Logistic regression may be a bit slow in terms of processing, but it can be very effective at separating data into two groups, and understanding how the sigmoid function works gives you a lead into neural networks. So that's good. The naive Bayes set of algorithms tend to be fast, but not necessarily the most accurate. I like using a naive Bayes implementation early on, just to get a feel for whether I've got a shot at hitting expectations around accuracy and model quality. The idea is that I perform a little bit of pre-processing, and then train a naive Bayes model using whichever of the algorithms makes the most sense. If I'm in the ballpark of acceptable, that's a good sign that it makes sense for me to dig in, performing more data processing, trying out more expensive but more capable algorithms, those sorts of things. If I'm nowhere near the mark, this is not necessarily a sign that other algorithms would fail, but it is relevant information that I can bring back to the person or group paying for my services, and we can have one of those tough discussions earlier on in the process. When it comes to passive-aggressive algorithms, they have some strong upside. They train very quickly and can be quite accurate. Going back to my story time from earlier, while most of the team was struggling to train random forest models on our laptops, one of our team members tried a completely separate approach in training a passive-aggressive classifier, and he got immediate success. It ended up being not the most accurate model of the bunch, but it was close to the top and required little in way of resources. We actually spent a few weeks as a team digging further into the literature on online passive-aggressive algorithms and hand implementing a couple of the later papers that claimed improvements over the base classifier, though Sadly, in our scenario, the updates didn't actually improve model quality. Still, it showed us that this algorithm can train well on limited hardware, and in production scenarios, I'd say they would be a great choice for something like an embedded device where memory is at a premium. But passive-aggressive algorithms have two serious downsides. The first is that they can be prone to sequencing failures, especially if your dataset has a natural order. Make sure to shuffle up that data well before feeding it into the algorithm for training. The second problem is that passive-aggressive algorithms may struggle with multi-class classification scenarios, as they don't do nuance very well. You'll typically find a lot more success with two-class scenarios. Finally, the last thing that I want to mention, one final reminder that accuracy is not the ultimate measure. It may be a very useful first measure, but make sure to take full advantage of the confusion matrix, particularly if you have reason to believe that you are working with imbalanced data. And that's going to do it. We are closing the books on this series on classification. In the next episode, I'm going to start a brand new series. But if you liked this series and you want me to cover a particular topic, let me know in the comments and I might create a coda video. I greatly enjoyed putting together this series, and I hope you did as well in viewing it. We'll have links and show notes in the description below. Until we see each other in the next video, take care.